Welcome to a new episode on the Technomora channel. We really hope you will enjoy watching it and invite you to tell us what you think of it by leaving your reactions below the video. And now, please allow me to present your host, Technomora.
Thank you, Julie, for the introduction to part 2 of restoring and repairing the Bang & Olufsen 901. I don't know what happened in the past with the Beomaster 901, but the crux of the matter is that the end stage was not good at all. And you'll remember that one of the electrolytics had been replaced, okay? And one of the diodes, the current limiting diodes, I think it was on the left channel, was placed incorrectly. So the current limiting would never have worked, at least with this channel, to be sure. Now, it turns out that specifically the PNP end stage transistors were not good. I forget which one is the PNP and which one is the MPN. I'm sure I can find it back somewhere. In any case, either one of these two is the PNP, and it seems the PNP end stage transistors, well, they're just pop, just like that. In fact, I replaced the transistors of the left channel first, so I switched to a heavier model PNP, namely BD650. And that seems to work out okay. I also replaced the end stage power resistors. So the end stage resistors are 0.39 ohms. Okay, there you go. So 10%. And I bought the identical resistors, the same brand and everything, to replace the original ones. Okay, so the only big difference is that these ones here do not have that little metal bracket you see on the original one. Okay. Also, I did replace these resistors because they are far lighter in build than the new ones. And in fact, one of these burned up while there was a thermal runaway. So I had to replace the one, and then I thought, well, if I'm going to replace the burnt one, then I might just as well replace the other one, even if it's supposedly still good. So there you go. Yeah, for some reason the end stage of the Beomaster has been seriously compromised. So I replaced the end stage transistors with, for the PNP side, BD650, and for the NPN side of the push-pull, BD644. Okay, I'll list the specifications at the end of the video, or below it, as it may be. So yeah, now the two outputs seem to work, although they are a bit quiet. And in fact, when I push the volume to maximum, I get a reasonable amount of sound out of the speakers, but really it's awfully quiet. They should be screaming loud. So I need to find out what is or what could be improved. Alright, I replaced the output transistors of both channels of the Beomaster 901, and the reason being that both channels were subjected to what is called in engineer parlance thermal runaway, and in fact they were certainly the both PNP transistors on the both output channels were damaged because of that. These, in fact, are the transistors that I replaced, okay? So TR22 and TR23, okay? And they use both the same type of transistors on both sides, alright? And the original transistors look like this. So a BD697 and a BD698. Now, these original Motorola output transistors, I could have bought them, but they are going for a ridiculous price on the internet, and I refuse to pay such a ridiculous price. So I shopped around for power transistors that would probably do the trick, and I found for the PNP side a BD650, and for the NPN side a BD645, and they seem to work, I think, correctly, as they should. They don't get excessively hot. The only problem I have right now is that I need to crank up the volume all the way to get a decent volume out of the output, and that's not right, of course. So I need to investigate how I can make the output of the amplifier screaming loud. If you're curious to know what the transistors look like that I use to replace the old power transistors with, well, this is one of them. Okay, now this happens to be a Russian one, a BD644, but I didn't use this particular model anyway. So this is a PNP transistor. I used a BD650 rather than a 644. Now you can tell that the form factor of both types of power transistors is completely different. However, it turns out that mounting these ones, doesn't represent a problem. Okay, so they fit exactly in the same spot as the original transistors. All you need to do is to bend the legs of the replacement power transistor to the same shape as the original ones. Yeah, and that's about it. So all you need to take care of course, is to use micas to insulate the transistor from the heatsink body. Okay, so this is the original heatsink that was mounted to the power transistor. So I'm going to mount the original one back, and this is only a temporary one I mounted, on the small power regulated transistor, which is, by the way, a BD239 if I'm not mistaken, also a PNP. So yeah, there you go. Replacing the original one, the original transistors, okay, with replacement power transistors is no problem at all. There's no point in using tons and tons of heat-based, heat conductive paste on a heatsink or on the micas you're going to place back, like this. Alright, so the whole idea of the heatsink paste is to aid in conducting or enlarging actually the surface through which the heat can be dissipated in the heatsink, right? So, like the name implies, this paste improves the conductivity towards heat of the heatsink, alright? But you don't need a huge amount of the paste, you just need enough paste on both sides of the mica and on the heatsink and on the transistor, and just to allow the heat to be dissipated a bit easier through the heatsink, and that's it. So applying like a ton of this on either side of the transistor won't improve noticeably the heat exchange. In fact, it might even make it worse in a sense. Yeah. The whole goal is to have an ultra thin layer of heat conduction, of good or perfect heat conduction between the transistor and the heatsink. And that's what that paste is intended to do, nothing more. Alright, I mounted back the screws that squeeze, as it were, the heatsink against the power transistors. Now, the heatsink has a little tab there. You can just about see it, which fits in a hole on the side of this metal bracket. And it also has a hole there which fits onto this bracket here, and you need to tighten it up with this screw. Okay, it's not a Phillips screw, just a normal M3 screw. By the way, all the screws that hold the heatsink against the power transistors are all M3 screws, painted black, and also there's a little nylon spacer between the screw and the heatsink, and that is important. Okay, so under no circumstance should the power transistor make electrical contact with the heatsink, because the heatsink is attached to ground, in fact, to the chassis. Okay, so yeah, don't make the mistake of not putting nylon washers, special washers for heatsinks down there. If you don't, you'll have a big boom. Alright, I'm measuring the temperature of the power resistors now. You can see where I'm shining the laser at, and the temperature is 30 degrees of those ones, and a little bit more than 31 degrees on those. The volume is on 0 for the moment, so this is one of the power regulators. 39 degrees Celsius, by the way. So yeah, that is not very warm. In electronic terms, that's really rather cool. Strangely enough, though, the coil, which is, you see, lighted by the laser over there, is to transmit heat from one of the collectors of one of the power transistors to the current limiting transistors of the right channel, I think this is. Yeah, the right channel. So, and that says it's at 36 or so. Yeah, something like that, 36 degrees. Whereas the other one down there, yeah, you can barely see it, but it's over there. That one only is slightly more than 30 degrees Celsius. Now, strangely enough, the part that heats most in this amplifier tuner is right down here, in fact. So this resistor down there, okay, so, and that heats up to 50 degrees Celsius. And if I shift a little to there, that resistor, okay, that one I'm shining my laser on, yeah, that one goes all the way to 60 degrees C. So strangely enough, the part you're seeing right there heats up most in the tuner. So I need to figure out what that part exactly does and why it would be so warm. Alright, so using the mono switch on the amplifier, I determined that the problem is definitely not in the end stage of the amplifier, which is good. So we also determined that the left channel was kind of thinny sounding, and there was also quite a bit of buzzing going on. Now, if you look on the schematic, okay, you can tell that the tape and phono input, which are here, so tape, phono, go, in fact, into these three stages here, and I say three because there are three. So it goes into an amplification stage, you see here. Then in a second amplification stage, which is immediately followed by a whole lot of filtering for treble and bass, okay? And then this filtered signal goes on to a, you could say, a final amplification output stage, which is this transistor here, 2TR18. And from there on, the sound goes to the volume slider potentiometer, and from there to the balance slider potentiometer. Okay, now having tested the mono setting, or switch rather, we do know that the sound arrives all the way to the volume and the balance potentiometers. So we might consider that this transistor, the 2TR18, is probably good. So, and we're looking at the left channel, okay? So then the next question is, alright, now that we determined the end stage transistor is probably running fine, which of these two is causing us trouble? Alright, now those three transistors I'm showing you are located right here. Let me see if I can show you. So right there where I'm shining the laser, okay, that's 2TR16, okay, this transistor here. And this transistor is a BC148. I don't know if you can see it, but there you go. Alright, so it's a BC or BC149 maybe, I can't tell but from here, but I think it's maybe 149. Okay, so that's 2TR16. Now 2TR17 is down there. Alright, so it's that little dome transistor you see here, okay, on which I'm shining my laser. Right there. Okay, so this little dome transistor here is 2TR17. Okay, and then we move on to 2TR18, and 2TR18 is where are you? Here it is. So 2TR18 is down there. Okay, so it's this one here where I'm shining my laser. Okay, so this is 2TR18. Alright, so one of those three transistors is causing us trouble, and I'm suspecting it's either 2TR16, which is down there, or 2TR17, which is down there. Yeah. So what I'm going to do, if you look at the schematic, so if you look at the schematic, what I am going to do is inject a signal to the base of 2TR18, then a signal to the base of 2TR17, and then a signal to the base of 2TR18. Now, if I inject a signal here and it comes out loud and clear from the left output channel of the amplifier, then obviously there's no problem downstream. If, however, there is no adequate amplification, then I must inject the sound here and see whether the output stage, the left output stage, is still outputting sound, okay, adequate sound. If it isn't, then there is a problem possibly with this stage. So if we move on and I inject a signal here, and the left output channel of the amplifier is still quiet, then in all likelihood there is a problem with this transistor. I forgot to mention that when I say the left channel for phono and tape do not work, that's maybe a bit of a misnomer. Yeah, the left channel does work, but it's very, very faint. So I need to find out why that is. Is it a mechanical problem, or is it an electronical problem? The tuning mechanism seems to consist of a stereo indicator and then two tuning direction indicator bulbs. Okay, so if I'm on a radio station right now, and it's playing a stereo signal, obviously. Now, watch the two bulbs on the left as I detune slightly in one and in the other direction. You see how they alternate in strength? So, and if I make them light up equally, the stereo indicator comes on. So basically what Bang & Olufsen wanted to do is give you a visual cue as to how well tuned you are to a specific radio station, and that's kind of cute. I've never seen this sort of tuning mechanism before. The kind of light bulb it uses is this. Alright. And these are light bulbs used in dashboards of cars mainly, but I seem to remember they are also used in dashboards on boats, pleasure boats. So yeah, you can get these in 6.3 volts. You can also get them for 12 volts and even for 24 volts. So even though the shape is the same, the working voltage is definitely not. So before you buy these, make sure that you buy the right type. I'm going to give the Beomaster 901 an AM alignment, and I'm following pretty much the instructions of the service manual, and basically they instruct me to inject a modulated 460 kilohertz signal into the radio, but instead of using a direct signal injection like they prescribe here, I'm going to use a coil induction method. So an indirect coupling, you could say. And it's relatively easy actually, so all I need to do is follow the instructions and set these little tuning transformers or tuning coils here in the order they prescribe. So 1, 2, 3, 4, 5, etc. And they do say that measuring with an oscilloscope on these pins here should give a maximum signal. So if you look closely, come on, focus. Why won't you focus? There. So they do say that the signal you measure here on the oscilloscope should be a maximum. And they also say that you need to turn the ferrite cores of these little transformers to get a symmetrical maximum. okay, and they do say in the order 1, 2, 3, 4, 5, 6, and that's exactly what I'm going to do. So give me a moment to set up the camera to show you the oscilloscope, and then we'll get on it. Alright, so I marked the original positions of the ferrite cores of the little high frequency transformers you see in the center of the image with a red marker, a red alcohol marker, just in case I would need to return to the original position. Also, I'm going to turn the cores of these little transformers with a special little screwdriver which has a plastic handle, okay, and a ceramic tip. So this is non-conductive, okay. There you go. That's the brand. So you need to use a non-conductive screwdriver to turn the cores of those little transformers, alright? If you use a metal screwdriver, well, the signal might be a bit offset because of that, yeah, because a metal part will create a magnetic field, basically. Okay, I am injecting a 468 kilohertz signal modulated at 400 hertz via a little coil. You see here a coil of 20 gauge wire. I'd say about 25 turns, okay, and I inject the signal directly into the AM section of the radio, but not by electrical coupling, but rather, as they say I should, but rather via indirect induction, and that works just as fine, I believe. Now, I did hook up the oscilloscope to these 2 points here, and when I say these 2 points, I mean those 2 points, alright? You see them right here, okay? So this and the ground is here. So there are two basically there are 2 tabs to which you can attach your oscilloscope, and I set it to auto level. Alright, I mean the oscilloscope. Okay, so they ask us first to turn 1 and 2, which are this core and that core, counterclockwise until I get a maximum signal on the oscilloscope. Alright, let's do that. So 1 and 2 are this one and that one. Okay? So that's what I'm going to do next. Alright, I went back and forth turning all the cores of the IF transformers in sequence, so from 1 to 5, and in the advised direction until I got a nice symmetrical maximum on the oscilloscope, and that's what I'm getting, a nice symmetrical strong signal on the oscilloscope. And yeah, these interferences come from any other high frequency equipment in the neighborhood. Okay, so anyway, as you can tell by the sound of the radio's output, it's a good strong 400 Hertz reference signal I'm hearing. Well, yeah, reception is marginally better, but keep in mind there's a lot of equipment around the tuner, and that is interfering terribly with the reception. Yeah, so unfortunately, the only way to test the AM part of the tuner would be to place the tuner in a totally electrically quiet environment. Alright, I'm getting ready to set the rest current on the power transistors, and to do that I soldered two small eyelets to the power resistors pins over which I need to measure a voltage drop. Okay, and you can see I hooked up my multimeter on the right channel's power resistor, but not yet on the left one. Alright, now the power resistor I'm talking about is in fact this one right here. Okay, so this is for the right channel. Okay, so you need to hook up the measurement leads of your multimeter over the pins of this precise resistor, and the other resistor you need to measure over is, let me see, yeah, is this one. This is for the left channel, and this one is for the right one, and to be more precise, I seen from here it's R. For the right channel, it's R191. Alright, you see it down there. Okay, so I hooked up my multimeter to the pins of that power resistor, and I'm going to switch on the amplifier and put the volume on minimum. Okay, there you go. So give it a minute to stabilize. Right, so the volume is at absolute minimum. Alright, so now you can tell the voltage drop over that power resistor, so R191, is let me see, 10.3 millivolts. Alright, now according to the service manual, the voltage drop over that power resistor should be exactly 10 millivolt with zero volume, so totally quiet. Now the way to set that is to use this potentiometer right here. Okay, so I don't know if you can see it, guys, but let me show you. So this one here. Okay. Alright, so I'm using a tiny screwdriver to turn the potentiometer around until we get 10 millivolts on the multimeter. Now, if you do this, be very, very gentle. alright, and give the amplifier some time to heat up, as it were. Yeah, a couple of minutes or so. And that way you can set the voltage very accurately. Now, when I say go easy, I really mean go easy. Yeah, so just give it a little twist to the left or the right, and you see it's very, very touchy until you get close to 10 millivolts. Alright, so but as you can tell, it's extremely touchy. So, and you need to be really careful, because if you put too much current through the end stage transistors, they'll go into thermal runaway and they'll literally burn up. Alright, I think I will cut episode 2 short here, because it's becoming a bit too long, I think. My conclusion is there's still a problem with a certain amount of distortion, either on input or output. I haven't traced that yet. There's also apparently a problem with the left channel of the output of the tuner. Yeah, when I select the FM tuner and I leave it on stereo, the left channel comes through very weakly. Whereas if I select mono, the mono mode on the amplifier, both outputs play just as loud and as good. Whereas if I select stereo, then the left channel of the FM tuner becomes very weak in comparison to the right channel. So I need to figure out what could be the cause of that problem, but that will be for a next episode. So I would say thanks for watching, and I'll see you with pleasure on the next episode, the last episode of restoring the Beomaster